Before time existed, before space had meaning, before the universe took its first breath, there was something. Or maybe there was nothing. Or perhaps that question itself breaks down when applied to a moment that sits outside everything we understand as reality. For decades, physicists treated the Big Bang as the ultimate beginning, the point where all questions stop and explanations end. The moment when the universe simply started existing, and asking what came before made no more sense than asking what's north of the North Pole. But science has a way of refusing to accept walls, even walls built from logic itself. And now, after years of theoretical work, mathematical breakthroughs, and observations that peer deeper into cosmic history than ever before, we're finally assembling an answer. Not a complete picture, not a final truth, but something far more interesting. A coherent framework that lets us think seriously about what preceded the Big Bang without collapsing into nonsense. If you're curious about the edge of knowledge itself, subscribe and hit that like button, because what we're about to explore sits at the absolute frontier of human understanding. The story of what happened before the Big Bang begins, strangely enough, with Einstein's greatest mistake, or at least what he called his greatest mistake. In the early 20th century, Einstein's equations of general relativity revealed something unexpected about the universe. The equations didn't allow for a static cosmos. Space itself, according to the math, had to be either expanding or contracting. It couldn't just sit still. This bothered Einstein deeply. At the time, every astronomer believed the universe was eternal and unchanging. The idea that it might be growing or shrinking seemed absurd, almost philosophical rather than physical. So Einstein did something unusual for him. He modified his own equations, adding a term he called the cosmological constant, a kind of anti-gravity that would hold the universe in perfect balance, preventing collapse or expansion. It was an elegant patch, mathematically speaking, but it felt wrong even to him. Then, in the late 1920s, an astronomer named Edwin Hubble made a discovery that changed everything. By studying distant galaxies, Hubble noticed something strange. Light from those galaxies was shifted toward the red end of the spectrum, and the farther away a galaxy was, the more its light was shifted. This redshift had a clear interpretation. Those galaxies were moving away from us, not just drifting randomly, but receding in a pattern that suggested the entire universe was expanding. Every region of space was stretching, carrying galaxies apart like dots on an inflating balloon. Einstein's equations had been right all along. The universe wasn't static. It was dynamic, evolving, growing larger with every passing moment. And if space is expanding now, that means it was smaller in the past. Much smaller. Run the clock backward far enough, and you arrive at a moment when all of space was compressed into an unimaginably small, hot, dense state. That moment became known as the Big Bang. But calling it a bang is misleading. There was no explosion in the traditional sense, no detonation that sent matter flying outward into empty space. Instead, space itself began expanding from an initial state of extreme density and temperature. The universe didn't explode into space. Space itself was born in that moment, or so the standard story goes. This framework explained an enormous amount. It predicted the cosmic microwave background, a faint glow of radiation left over from when the universe was young and hot. It explained why the universe contains the specific mix of hydrogen, helium, and other light elements that we observe. It accounted for the large-scale structure of galaxies and the way matter is distributed across the cosmos. For decades, the Big Bang model was physics's most successful cosmological theory. But it came with a problem, a deep one. The equations that describe the Big Bang break down as you approach the initial moment itself. As you rewind time closer and closer to the beginning, densities and temperatures rise without limit. The math predicts a singularity, a point where the laws of physics as we know them simply stop working. Singularities are places where equations produce infinities, where predictions become meaningless, where the framework collapses. General relativity, the theory that describes gravity and the structure of space-time, cannot handle singularities. It treats them as boundaries beyond which nothing can be said. And that means the Big Bang, as described by classical physics, is not actually an explanation for the universe's origin. It's a description of what happened after some initial condition that the theory itself cannot address. This limitation became increasingly uncomfortable as cosmology matured. The Big Bang wasn't wrong, but it was incomplete. It answered what happened once the universe got started, but it offered no insight into how or why it started in the first place. For a long time, many physicists simply accepted this. The origin of the universe might be inherently unknowable, sitting forever outside the reach of science. But that resignation began to crack in the late 20th century as two major developments converged. The first was the rise of quantum mechanics as a fundamental framework for understanding reality at the smallest scales. Quantum theory had already revolutionized physics by showing that particles, energy, and even space and time behave in ways that defy classical intuition. Uncertainty, probability, and fluctuation became essential features of nature, not just measurement limitations. The second development was the realization that gravity, the force governing the universe's large-scale structure, must also have a quantum description. General relativity is a classical theory, meaning it treats space-time as smooth and continuous. But at extremely small scales, near the Planck length, space-time itself should exhibit quantum behavior, becoming grainy, uncertain, and fluctuating. Combining quantum mechanics with general relativity has proven to be one of the hardest problems in physics. The two frameworks resist unification. But physicists began asking a provocative question. What if the singularity at the Big Bang isn't real? What if it's an artifact of using classical equations in a regime where quantum effects dominate? If space-time itself becomes quantum near the Big Bang, then the singularity might dissolve into something more subtle, something that allows time and causality to extend backward beyond what classical physics permits. This line of thinking opened the door to pre-Big Bang cosmology. Instead of treating the Big Bang as an absolute beginning, these new models suggest it might be a transition, a boundary between different phases of the universe's evolution. What we call the Big Bang could be the moment when a previous state of the cosmos transformed into the expanding universe we observe today. That shift in perspective is profound. It means the question, what happened before the Big Bang, stops being nonsensical and starts being scientific. It's no longer asking what came before time itself. It's asking what state the universe was in during a phase we haven't yet observed directly, a phase hidden behind the energies and densities where our current theories break down. Several theoretical frameworks now offer specific, testable ideas about what that earlier phase might have looked like. One of the most influential is called eternal inflation, though the name is somewhat misleading because it doesn't mean inflation lasts forever in time. Rather, it means inflation is ongoing in some regions of space, even as it ends in others. Inflation itself is a well-established concept in cosmology. It refers to a brief period in the universe's early history when space expanded exponentially fast, far faster than the ordinary expansion we observe today. This rapid inflation smoothed out irregularities, stretched quantum fluctuations into the seeds of galaxies, and solved several puzzles about why the universe looks the way it does on large scales. But eternal inflation takes this idea further. It suggests that the inflating state is not something that ends everywhere at once. Instead, inflation continues in some regions while stopping in others. Where it stops, a bubble of normal space forms, expanding and cooling into something that resembles our observable universe. Where it continues, the inflating region keeps growing, eventually spawning more bubbles. Each bubble becomes its own distinct universe, with potentially different physical properties. This process has no clear beginning. Inflation could have been occurring eternally into the past, producing an infinite number of universes across an ever-expanding multiverse. In this picture, our Big Bang was not the origin of everything. It was the moment inflation ended in our particular bubble, allowing matter, radiation, and familiar physics to take over. What we call the beginning was really just a local phase transition, one event among countless others occurring throughout a much larger structure. This framework solves the singularity problem by removing the need for an absolute origin. There is no first moment because inflation extends backward indefinitely, but it introduces new puzzles. If inflation is eternal, why does it ever end in any given region? And if it's been going on forever, producing infinite universes, how do we make sense of probabilities and predictions within such a framework? These questions remain unresolved. The mathematics behind eternal inflation is fascinating and complex. The inflaton field, a hypothetical scalar field responsible for driving inflation, has a potential energy landscape. Think of it like a ball rolling down a hill. In most regions, the ball sits high on the hill, causing rapid expansion. But quantum fluctuations can push the ball in different directions. In some patches of space, these fluctuations push the ball down the hill, ending inflation and creating a bubble universe. In other regions, fluctuations push it back up or sideways, prolonging inflation. The key insight is that the expanding regions grow so fast that they always outpace the regions where inflation ends. Even though bubbles are constantly forming, the total volume of inflating space keeps increasing. This creates a fractal structure, an infinite foam of bubble universes embedded in an eternally inflating background. Each bubble universe could have different properties. The fundamental constants of nature, the masses of particles, even the number of spatial dimensions might vary from bubble to bubble. This diversity arises from how the inflaton field decays into matter and radiation. Different decay pathways produce different physics. In some bubbles, stars might never form because gravity is too weak. In others, atoms might be unstable. Our universe, with its particular set of constants, is just one possibility among an infinite ensemble. This multiverse scenario has profound implications. It suggests that the properties of our universe, which seem finely tuned for life, might not reflect deep principles but statistical accidents. We observe these particular values because only in universes like ours can observers exist to do the observing. This anthropic reasoning is controversial. Some physicists embrace it as a natural consequence of eternal inflation. Others reject it, arguing that science should explain why things are the way they are, not just why we happen to find ourselves in a universe where we can exist. Another approach avoids eternal structures by proposing that the universe undergoes cycles. Instead of beginning with a singularity, the cosmos bounces between phases of expansion and contraction. In this cyclic model, our Big Bang was not the first. It was preceded by a contracting phase, during which a previous universe shrank down toward a highly compressed state. But instead of collapsing into a singularity, quantum effects intervened, causing the universe to bounce back into an expanding phase. That bounce is what we observe as the Big Bang. The contracting phase before the bounce could have lasted for billions of years, or it could have been brief. Either way, it avoids the singularity by replacing it with a smooth transition. Cyclic models are elegant because they eliminate the need for a beginning entirely. The universe has always existed, oscillating through endless cycles of expansion and contraction. Each cycle might look similar, or they might differ dramatically depending on how matter and energy behave during the bounce. One challenge for cyclic cosmologies is entropy. The second law of thermodynamics states that disorder or entropy always increases over time. In a cyclic universe, you would expect entropy to accumulate across cycles, eventually producing a universe filled with maximum disorder and no structure. How do cycles reset entropy if they do at all? Some models propose mechanisms for entropy to be redistributed or diluted during the bounce, but this remains an active area of debate. One specific cyclic model developed by Paul Steinhardt and Neil Turok addresses the entropy problem through a mechanism involving extra dimensions. In their scenario, our three-dimensional universe exists on a brane, a membrane-like structure floating in a higher dimensional space. A second brane exists nearby, separated by a small gap. The two branes attract each other gravitationally, and periodically they collide. Each collision releases enormous energy, creating the hot, dense state we call the Big Bang. After the collision, the branes bounce apart, and the universe expands and cools. Eventually, the expansion slows, stops, and reverses as the branes are pulled back together by gravity. They collide again, initiating another cycle. During each cycle, entropy does increase, but the expansion stretches structures apart, diluting the entropy density. By the time of the next collision, the universe is nearly empty and smooth, ready to begin again. This model makes specific predictions about the cosmic microwave background and the distribution of matter that differ slightly from standard inflation. Observations have so far been consistent with both models, but future experiments might distinguish between them. Another strength of cyclic models is that they explain why the universe appears flat and homogeneous without requiring an inflationary phase. The repeated cycles naturally smooth out irregularities over time. However, cyclic models face their own challenges. The bounce itself is difficult to describe mathematically. Classical general relativity predicts a singularity at maximum compression, just as it does at the Big Bang. To avoid this, cyclic models must invoke quantum gravity effects, and we don't yet have a complete theory of quantum gravity to work with. Researchers have explored various approaches, including loop quantum gravity and string theory, to model the bounce, but these efforts are still preliminary. Additionally, some versions of cyclic cosmology struggle with fine-tuning. The mechanism that allows bounces to repeat indefinitely requires very specific conditions. If the universe contracts too quickly or too slowly, the bounce might fail, leading to a singularity or an eternal contraction. Getting the parameters just right is non-trivial. A third class of models focuses on the quantum nature of spacetime itself. These approaches, often grouped under the label quantum cosmology, attempt to describe the universe's earliest moments using a quantum mechanical framework. In quantum mechanics, particles don't have definite positions or velocities until they're measured. Instead, they exist in a superposition of possibilities, described by a wave function. Quantum cosmology applies this idea to the entire universe. Instead of a single classical history, the universe is described by a wave function that encodes all possible histories. Most of these histories might be wildly different from what we observe, but some subset aligns with the universe we inhabit. One influential proposal within this framework is the no-boundary model developed by James Hartle and Stephen Hawking in the 1980s. In this picture, time itself becomes less definite near the Big Bang. As you trace the universe backward, time gradually transitions into something more like space, smoothing out in a way that eliminates the singularity. There is no sharp beginning because time doesn't extend infinitely into the past. It curves around, forming a closed surface with no edge. Asking what happened before the Big Bang is like asking what's south of the South Pole. The question assumes a direction that doesn't exist. This model is mathematically elegant and avoids singularities, but it requires a deep conceptual shift. Time is not a universal backdrop, but something that can change character depending on conditions. The no-boundary proposal uses a mathematical technique called the path integral, borrowed from quantum field theory. In this approach, you calculate probabilities by summing over all possible histories connecting an initial state to a final state. For the universe, there's no initial state in the usual sense. Instead, the path integral includes histories where time is imaginary, a mathematical trick that transforms time into a spatial dimension. In imaginary time, the universe has no boundary, no moment of creation. It's finite, but unbounded, like the surface of a sphere. When you translate back to real time, you recover a universe that appears to have a beginning, but that beginning is not a singularity. It's a smooth point where time starts. This model predicts a specific quantum state for the early universe, which determines the probabilities for different configurations of matter and energy. In principle, these predictions could be tested by comparing them to observations of the cosmic microwave background and large-scale structure. So far, the no-boundary proposal has had mixed success. Some of its predictions match observations reasonably well, but others are less clear. The model also faces technical challenges. Different ways of calculating the path integral can give different answers, and there's ongoing debate about which calculation is correct. Another quantum cosmology approach imagines the universe emerging from a quantum fluctuation in some pre-existing state. Even in what we might call nothing, quantum mechanics allows for temporary violations of energy conservation, producing brief flickers of matter and energy that vanish almost instantly. Most of these fluctuations are tiny and short-lived, but under the right conditions, a fluctuation could grow rather than collapse, expanding into a full universe. This idea is speculative and hard to test, but it illustrates how quantum mechanics allows for creation without a cause in the traditional sense. Causality, as we understand it, is a classical concept that may not apply at the quantum level where the universe began. The physicist Alexander Vilenkin has developed a related model called tunneling from nothing. In quantum mechanics, particles can tunnel through energy barriers that classical physics would forbid them from crossing. Vilenkin applies this idea to the universe itself. In his model, the universe begins in a state of nothing, which he describes as a closed geometry with no space or time. Through quantum tunneling, this nothing transitions into a tiny, expanding universe. The tunneling probability can be calculated using the path integral, and the results suggest that universes can spontaneously appear from nothing with some finite, if extremely small, probability. This raises deep philosophical questions. If the universe can create itself from nothing through quantum processes, does that eliminate the need for any external cause or creator? Some scientists and philosophers argue that it does, while others point out that even quantum tunneling relies on pre-existing laws of physics. Where do those laws come from? And what exactly is nothing if it has properties like quantum fluctuations? These debates touch the boundary between physics and metaphysics, and there's no consensus on the answers. All of these models, eternal inflation, cyclic cosmologies, and quantum cosmology, share a common feature. They push the boundary of explanation backward, but they don't necessarily eliminate the boundary. Eternal inflation delays the origin indefinitely. Cyclic models eliminate it by positing infinite cycles. Quantum cosmology smooths it out or redefines it. But none of them answer the ultimate question of why there is something rather than nothing. They offer frameworks for what preceded the Big Bang, but they still assume some underlying structure. Physical laws, quantum fields, space-time itself. Where do those come from? This question touches the edge of physics and philosophy. Some physicists argue that asking why about the universe's existence is inherently unanswerable, because any explanation would require prior assumptions that themselves need explaining. Others suggest that the laws of physics might be necessary in some deep sense, meaning they couldn't have been otherwise. Still others entertain the possibility that the laws themselves evolved or emerged from an even more fundamental substrate. What makes these questions scientific rather than purely philosophical is that many pre-Big Bang models make predictions that can, in principle, be tested. Eternal inflation, for instance, predicts certain patterns in the cosmic microwave background radiation. Specifically, it predicts a nearly scale-invariant spectrum of fluctuations, meaning that the amplitude of fluctuations is roughly the same at all scales. Observations from satellites like WMAP and Planck have confirmed this prediction with impressive precision. However, eternal inflation also predicts the existence of other bubble universes, which are by definition beyond our observational reach. This makes the multiverse aspect of eternal inflation difficult to test directly. Cyclic models predict subtle signatures in gravitational waves. During the bounce, when the universe transitions from contraction to expansion, gravitational waves should be produced with a characteristic spectrum. Future gravitational wave detectors such as the Laser Interferometer Space Antenna, or LISA, might be sensitive enough to detect these primordial waves. If observed, they would provide direct evidence for a pre-Big Bang phase. Cyclic models also predict slight deviations from the predictions of standard inflation in the cosmic microwave background. These deviations are small, but they could be detected with next-generation experiments. Quantum cosmology models might leave imprints in the large-scale structure of the universe. The no-boundary proposal, for example, predicts a specific initial quantum state that influences how matter and energy are distributed. By measuring the statistical properties of galaxy clustering and the cosmic microwave background, physicists can constrain which quantum cosmology models are viable. Some versions of the no-boundary proposal have already been ruled out by observations, while others remain consistent with the data. None of these signatures have been definitively detected yet, but the fact that they could be observed means these ideas belong to science, not just metaphysics. The universe is not hiding its history from us. It's written in the light we detect, the structures we map, and the laws we uncover. Every observation refines our understanding, narrowing the space of possibilities and guiding us toward the truth. One of the most promising observational tools is the cosmic microwave background itself, the ancient light left over from when the universe was roughly 380,000 years old. This radiation has been mapped in exquisite detail by satellites like COBE, SAWMAP, and Planck, revealing tiny temperature fluctuations that reflect quantum fluctuations in the early universe. These fluctuations were stretched by inflation and later became the seeds of galaxies. By analyzing the precise statistical properties of these fluctuations, physicists can infer details about the inflationary process and potentially glimpse features that arose even earlier. For instance, some models predict a specific pattern of polarization in the microwave background, a swirling pattern called B-mode polarization caused by gravitational waves generated during inflation. Detecting this pattern would confirm inflation and provide clues about the energy scale at which it occurred. If the energy is high enough, it might even probe physics from the pre-Big Bang era. In 2014, the BICEP-2 experiment announced the detection of B-mode polarization, sparking excitement that primordial gravitational waves had been found. However, subsequent analysis revealed that the signal was contaminated by dust in our galaxy, and the claimed detection was retracted. The search continues, with new experiments designed to filter out foreground contamination more effectively. If B-mode polarization is eventually detected, it will be one of the most significant discoveries in cosmology, providing a window into the universe's earliest moments. Another avenue involves gravitational waves, ripples in spacetime produced by violent cosmic events. Current detectors like LIGO and Virgo observe waves from black hole mergers and neutron star collisions. These detectors are sensitive to high-frequency waves, typically in the range of tens to thousands of hertz. Future detectors, including space-based observatories like LISA and ground-based facilities like the Einstein Telescope, will be sensitive to much lower frequencies, potentially revealing gravitational waves from the early universe itself. These primordial waves could carry information about phase transitions, cosmic strings, or other exotic phenomena that occurred near the Big Bang or before it. Primordial gravitational waves are different from the waves produced by astrophysical sources. They originate from quantum fluctuations in the fabric of spacetime during inflation or during the bounce in cyclic models. Because they were generated when the universe was extremely young and small, they have wavelengths comparable to the size of the observable universe today. This means they affect the largest scales in the cosmos, leaving imprints in the cosmic microwave background and the distribution of galaxies. Detecting such signals would offer a direct window into an era that no telescope can reach, because the universe was opaque to light before the microwave background formed. Gravitational waves, by contrast, travel freely through matter and radiation, carrying messages from the earliest moments. Even without direct detection, theoretical progress continues to refine pre-Big Bang models. Advances in string theory, loop quantum gravity, and other approaches to quantum gravity are providing new mathematical tools for describing spacetime at extreme energies. These tools allow physicists to explore regimes where classical descriptions fail, potentially revealing how the universe transitions from one phase to another without encountering singularities. String theory, for instance, suggests that the fundamental constituents of reality are not point particles, but tiny, vibrating strings. These strings exist in a higher dimensional space, most of which is compactified into shapes too small to observe directly. In this framework, the Big Bang might represent a transition between different compactifications, a moment when the geometry of extra dimensions changed, triggering the expansion we observe. String theory also introduces the concept of brane cosmology, where our universe is a three-dimensional brane embedded in a higher dimensional space. The Big Bang could result from a collision between branes, as in the cyclic model mentioned earlier. Alternatively, it could arise from the decay or splitting of a higher dimensional object. These scenarios are speculative, but they demonstrate how string theory provides a richer landscape of possibilities for understanding the universe's origin. Loop quantum gravity, another candidate for a quantum theory of gravity, treats spacetime itself as woven from discrete loops. At the Planck scale, around 10 to the minus 35 meters, spacetime becomes granular, and the smooth continuum of general relativity breaks down. In this picture, the Big Bang singularity is replaced by a quantum bounce, where the universe contracts to a minimum size determined by the granularity of spacetime, and then expands again. The contraction phase could extend arbitrarily far into the past, forming a bridge to a previous universe. These frameworks are incomplete and face significant challenges, but they demonstrate that the question of what happened before the Big Bang is not only sensible, but actively being pursued with rigorous mathematical and observational tools. The deeper we probe, the more it becomes clear that the Big Bang was not a true beginning, but a dramatic event within a larger, more complex story. What makes this era of cosmology so exciting is that we're not just speculating. We're building models, making predictions, and searching for evidence. Consider what we've learned just from the cosmic microwave background. By measuring its temperature fluctuations to extraordinary precision, physicists have determined the age of the universe, its composition, and its geometry. We know the universe is 13.8 billion years old. We know it's made mostly of dark energy and dark matter, with ordinary matter comprising only about 5%. We know space is flat to within measurement precision, meaning its geometry is Euclidean on the largest scales. These facts weren't known a century ago. They weren't even suspected. They emerged from careful observation and theoretical interpretation. And now we're pushing those techniques further, using the same methods to probe even earlier times, closer to the boundary where classical physics gives way to quantum uncertainty. Another clue comes from the distribution of galaxies across the universe. On the largest scales, galaxies are not scattered randomly. They form a cosmic web of filaments and voids, a structure that reflects the initial conditions of the universe amplified by gravity over billions of years. By mapping this structure in 3 dimensions, astronomers can trace its origins back to quantum fluctuations during inflation. The specific pattern of clustering carries information about the physics of the early universe, including hints about what preceded the Big Bang. For instance, if the universe underwent a cyclic bounce rather than emerging from a singularity, the statistical properties of those initial fluctuations might differ subtly from what standard inflation predicts. Detecting such differences would provide direct evidence for a pre-Big Bang phase. Large-scale structure surveys like the Sloan Digital Sky Survey and the Dark Energy Survey have mapped millions of galaxies, revealing the cosmic web in unprecedented detail. Future surveys, including the Vera Rubin Observatory and the Euclid mission, will extend these maps even further, measuring the positions and properties of billions of galaxies. By analyzing the clustering of these galaxies and the subtle distortions caused by gravitational lensing, cosmologists can constrain models of the early universe with ever-increasing precision. Similarly, the abundance of light elements, hydrogen, helium, and lithium, tells us about the conditions during the first few minutes after the Big Bang. The ratios of these elements match predictions from Big Bang nucleosynthesis with remarkable precision. However, there's a long-standing puzzle known as the lithium problem. Observations of the oldest stars show less lithium-7 than Big Bang nucleosynthesis predicts, a discrepancy that has persisted despite decades of effort to resolve it. Some researchers speculate that this anomaly could trace back to processes occurring before or during the transition we call the Big Bang. For example, if the universe underwent a brief period of non-standard physics just before nucleosynthesis, it could alter the production rates of light elements. Solving the lithium problem might provide indirect evidence for pre-Big Bang physics. Even the existence of dark matter and dark energy raises questions about pre-Big Bang physics. Dark matter is some form of matter that doesn't interact with light, but exerts gravitational influence. It outweighs ordinary matter by a factor of 5 and plays a crucial role in the formation of galaxies and large-scale structure. Dark energy is a mysterious component driving the universe's accelerated expansion. It accounts for roughly 70% of the universe's total energy and behaves like a cosmological constant, exerting negative pressure that pushes space apart. Neither is explained by the standard model of particle physics. Their origins might lie in the extreme conditions near the Big Bang, or in processes that occurred before it. For example, some models suggest that dark matter particles were produced during a phase transition in the pre-Big Bang universe, when the inflatoned field decayed into matter and radiation. Others propose that dark energy is a remnant of the inflationary field, a kind of echo from the era before the Big Bang ended inflation in our region of space. Testing these ideas requires combining cosmological observations with particle physics experiments. Detectors buried deep underground, such as those in the Xenon NT and LX Zeppelin experiments, search for dark matter particles colliding with ordinary matter. These experiments use tanks of liquid xenon surrounded by sensitive photomultiplier tubes to detect the faint flashes of light and ionization produced when a dark matter particle scatters off a xenon nucleus. So far, no confirmed detections have been made, but the experiments continue to improve in sensitivity, probing ever smaller interaction cross-sections. Particle accelerators such as the Large Hadron Collider smash particles together at high energies, hoping to recreate conditions similar to the early universe. By studying the products of these collisions, physicists search for new particles and interactions that might explain dark matter and other mysteries. While the LHC has not yet discovered dark matter particles, it has placed stringent constraints on many theoretical models. Future colliders, such as the proposed Future Circular Collider, could reach even higher energies, potentially unlocking new physics. Space-based observatories map the distribution of dark energy across cosmic history. By measuring how the universe's expansion rate has changed over time, astronomers can determine the properties of dark energy and test whether it's truly a cosmological constant or something more dynamic. Missions like the Dark Energy Spectroscopic Instrument and the Euclid satellite are designed to make these measurements with unprecedented precision, potentially revealing whether dark energy is evolving or interacting with other components of the universe. Each piece of data refines our picture, constraining models and ruling out alternatives. As we gather more evidence, certain models will survive while others fade. This is how science works, not by proving theories true, but by systematically eliminating those that fail to match reality. The models that remain standing become increasingly credible, not because they're the final truth, but because they're consistent with everything we've observed so far. One of the most profound shifts in thinking about pre-Big Bang physics is the realization that time itself might not be fundamental. In everyday experience, time flows steadily from past to future, providing a universal backdrop against which events unfold. But general relativity already showed that time is relative, flowing at different rates depending on gravity and motion. Clocks tick more slowly in strong gravitational fields and at high speeds. This time, dilation has been confirmed by countless experiments, from atomic clocks flown on airplanes to GPS satellites orbiting Earth. Quantum mechanics adds another layer, suggesting that time, like space, might emerge from something more fundamental. Some quantum gravity theories propose that space-time is not a basic ingredient of reality, but an emergent phenomenon, something that arises from deeper, more abstract structures. In this view, time and space only make sense in certain regimes, like the universe we inhabit. Near the Big Bang or before it, these concepts might not apply in the usual way. One approach, called causal set theory, treats space-time as fundamentally discrete, made up of elementary events connected by causal relationships. Time and space emerge from the statistical properties of these events, much like temperature emerges from the motion of atoms in a gas. This idea challenges our intuition deeply. We're accustomed to thinking of the universe as existing within time, with events happening in sequence. But if time itself is emergent, then the question, what happened before the Big Bang, might require a different kind of answer, one that doesn't rely on temporal sequence. It might be more like asking what conditions gave rise to the emergence of time, rather than what happened before time began. This shift is not just semantic. It changes what kind of explanations we seek and what kind of evidence we consider relevant. Instead of looking for a causal chain extending backward in time, we might look for structural principles or initial conditions that explain why the universe took the form it did. Philosophers and physicists have long debated whether science can ever explain existence itself. Some argue that any scientific explanation must assume some starting point, some prior framework, which itself requires explanation. By this logic, science can never close the explanatory loop. There will always be a deeper why that remains unanswered. This is sometimes called the problem of infinite regress. If the universe requires a cause, then what caused the cause? And what caused that? The chain seems to extend forever, never reaching a final explanation. Others counter that this critique misunderstands the nature of scientific explanation. Science doesn't seek absolute, self-contained answers. It seeks models that unify observations, make predictions, and deepen our understanding. Even if we can't explain why the laws of physics exist, we can still explore what those laws allow and how they shape reality. From this perspective, asking what happened before the Big Bang is not about reaching a final answer. It's about extending our understanding as far as possible, discovering new structures, and uncovering connections between seemingly unrelated phenomena. Each step forward reveals new questions, and that process is what drives science. What's remarkable about the current era is that these abstract questions are becoming empirically accessible. We're not just philosophizing about the origin of the universe. We're building instruments to probe it. The next generation of telescopes will peer further into the cosmos than ever before, detecting galaxies that formed mere hundreds of millions of years after the Big Bang. The James Webb Space Telescope, launched in 2021, is already observing some of the earliest galaxies, revealing how stars and black holes formed in the universe's infancy. Future telescopes, such as the Extremely Large Telescope and the 30-meter telescope, will push even further, potentially detecting individual stars in distant galaxies and studying the atmospheres of exoplanets for signs of life. These telescopes will also measure the properties of dark energy with unprecedented precision, constraining models of cosmic evolution. They will search for signatures of primordial gravitational waves, which would offer a direct glimpse into the universe's earliest moments. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2000s, will conduct wide-field surveys to study dark energy, dark matter, and the large-scale structure of the universe. By mapping how the universe has evolved over billions of years, these missions will test theoretical models and potentially reveal deviations from standard cosmology that point toward new physics. Particle accelerators, meanwhile, are pushing to higher energies, exploring physics at scales closer to those that governed the Big Bang. While we can't recreate the Big Bang itself, we can study the particles, fields, and interactions that existed then, testing whether our theories hold up under extreme conditions. The Large Hadron Collider has already discovered the Higgs boson, a particle that plays a crucial role in giving mass to other particles. Future experiments will probe the Higgs field in more detail, searching for hints of new physics beyond the standard model. Computational models are also playing a crucial role. Simulating the universe's evolution from the Big Bang to the present requires enormous computing power and sophisticated algorithms. These simulations test whether our theoretical frameworks can reproduce the observed universe, from the cosmic microwave background to the distribution of galaxies. When simulations fail to match observations, they reveal gaps in our understanding, pointing toward new physics. Advances in supercomputing and machine learning are enabling ever more realistic simulations, incorporating complex processes like star formation, supernova explosions, and black hole growth. All of this work is converging toward a more complete picture of the universe's history, including the pre-Big Bang era. We may never know every detail, but we're assembling a framework that's increasingly coherent, testable, and grounded in evidence. That framework suggests the Big Bang was not a beginning, but a transition, a moment when the universe shifted from one state to another, possibly part of a larger structure that extends beyond what we can observe. This realization is both humbling and exhilarating. Humbling because it reveals how much we still don't understand, how many assumptions underlie even our best theories, and how vast the cosmos is compared to our corner of it. Exhilarating because it shows that the universe is knowable, at least in part, and that human curiosity and ingenuity can reach across billions of years and unimaginable distances to touch the edge of existence itself. The question of what happened before the Big Bang is no longer a curiosity reserved for late-night philosophical discussions. It's a scientific question with theoretical models, observational strategies, and ongoing experiments. We may not have a final answer yet, but we have something better. A path forward, a set of tools, and a growing body of evidence that brings us closer with each passing year. As we continue this journey, we'll likely encounter more surprises. The universe has a habit of defying expectations, revealing structures and phenomena that no one predicted. Each discovery reshapes our understanding, forcing us to reconsider what we thought we knew. But that's the nature of science at its best. An open-ended conversation with reality, guided by evidence and disciplined by logic, always willing to revise its conclusions in light of new information. What happened before the Big Bang? We don't know for certain, not yet. But we know it's a question we can ask, and we're learning how to listen for the universe's answer. Whether that answer involves eternal inflation, cyclic bounces, quantum fluctuations, or something we haven't imagined yet, it will deepen our understanding of where we came from and what the cosmos truly is. And that pursuit, that relentless drive to know, is one of the most profound expressions of what it means to be human. Looking ahead, the next decade promises transformative developments. Gravitational wave observatories will open a new window on the early universe. Advances in quantum computing may enable simulations of quantum spacetime that were previously impossible. Each of these tools brings us closer to answering questions that once seemed permanently out of reach. But even as we push toward the ultimate questions, it's worth reflecting on how far we've come. A century ago, we didn't know galaxies existed beyond our own. We thought the universe was static and eternal. The Big Bang itself was considered radical, even absurd, by many scientists. Now it's textbook physics, and we're probing what came before it. That progress is staggering. It shows that the boundaries of knowledge are not fixed. What seems unknowable today may become routine tomorrow. The singularity at the Big Bang, once thought to mark the absolute limit of inquiry, is dissolving into a richer, more nuanced picture. We're learning to think about time, space, and causality in ways that transcend common sense, guided by mathematics and observation into realms where intuition fails but reason still applies. And as we explore these realms, we're not just learning about the universe, we're learning about the nature of explanation itself, about what it means to understand something, and about the limits and possibilities of human knowledge. These are deep questions, touching science, philosophy, and even meaning. What does it say about us that we can ask such questions? What does it say about the universe that it yields answers? Perhaps the most important lesson is that the universe is not arbitrary. It follows rules, and those rules are comprehensible. The same laws that govern atoms also govern galaxies. The same principles that describe the present also describe the past, extending back toward the Big Bang and potentially beyond. This coherence is not guaranteed. The universe could have been chaotic and lawless, but it isn't. It's ordered in ways that allow for prediction, understanding, and discovery. That fact alone is worth marveling at. The question of what happened before the Big Bang is part of a larger tapestry, a story that includes the formation of stars, the evolution of life, the emergence of consciousness, and the development of science itself. Each thread connects to others in unexpected ways. Understanding the early universe helps us understand how galaxies form, which helps us understand how stars evolve, which helps us understand how planets and life arise. Knowledge builds on knowledge, creating a structure that's far more robust than any single piece. This interconnectedness means that even partial answers about the pre-Big Bang era have implications far beyond cosmology. They inform our understanding of quantum mechanics, gravity, thermodynamics, and the fundamental nature of reality. They challenge us to think more carefully about time, causality, and existence. They remind us that the universe is deeper and stranger than we imagined. As we continue this exploration, we'll undoubtedly encounter setbacks and surprises. Some models will fail. Some observations will contradict predictions. Some questions will resist answers for longer than we'd like. But that struggle is part of the process. Science is not a straight path to truth. It's a winding journey with detours, backtracking, and occasional leaps forward. What matters is that we keep moving, keep questioning, and keep refining our understanding. The universe rewards persistence. It reveals its secrets slowly, layer by layer, to those willing to observe carefully, think deeply, and challenge assumptions. And so we find ourselves at a remarkable moment in history. For the first time, we're seriously investigating what happened before the Big Bang, using tools and theories that didn't exist a few decades ago. We're standing at the edge of a frontier that previous generations couldn't even approach. The answers we uncover will shape humanity's understanding of its place in the cosmos for centuries to come. They will tell us not just where we came from, but what kind of universe we inhabit. Whether it's eternal, cyclic, or something else entirely. Whether time is fundamental or emergent. Whether the Big Bang was a beginning or a transition. These are not abstract questions. They touch on the deepest aspects of reality, the structure of existence itself. And we're learning that we can answer them, not through speculation alone, but through observation, experiment, and reason. That's the power of science. It takes questions that seem hopelessly metaphysical and makes them empirical. It transforms wonder into understanding, mystery into knowledge, not by eliminating the mystery entirely, but by showing that even the most profound questions can be approached systematically. So, what happened before the Big Bang? The answer is emerging, piece by piece, from telescopes and accelerators, from equations and simulations, from the collective effort of thousands of scientists across generations. It's a story still being written, a question still being answered. But every day we get closer. Every observation adds detail, every theory sharpens our focus, and eventually we'll know. Not everything perhaps, but enough to see the Big Bang not as a beginning but as part of a larger story. One that extends beyond the boundaries we once thought absolute. That story, when fully told, will be one of the greatest achievements of human thought. It will represent our species' deepest inquiry into the nature of existence, a testament to curiosity, creativity, and the relentless pursuit of truth. And it starts here, now, with questions that once seemed unanswerable, but are slowly, methodically being addressed. The universe is vast, ancient, and strange, but it's not unknowable. We're proving that every day, pushing the edge of understanding further, reaching toward the ultimate questions. What happened before the Big Bang is one of those questions. And we're finally, after decades of groundwork, beginning to know. If you found this exploration of the universe's deepest mystery fascinating, make sure to like this video and subscribe, because science doesn't stop, and neither do we. The journey to understand existence itself continues, and you won't want to miss where it leads next.